Hi, so welcome to the next module. So we're going to continue to talk about drag a little bit. Okay, so we did derive some formula in the previous module in terms of how to evaluate a drag in terms of velocity, right? Now let us see what this exactly means. So if you remember, so this is the value that we were this is the relationship which we developed last time, right? So we said basically if you are able to now give an expression for this velocity, then one should be able to estimate the drag quite well, right? So let us see, let us sort of take a formula and see, take a little bit of a problem and see if that is even possible. So for example, let us take an expression for this u, right? This velocity, this is the free stream velocity, and see if that kind of even works. Okay. Now say we have a definition of u which is something like this. So u is right. So this n is basically a power, right. So this in the sense that the velocity is obeying some kind of a power law, as you can see it in terms of, and you can see that when y is equal to delta, delta is the usual boundary layer thickness. So when y is equal to delta, so u is equal to v infinity, right. So that kind of follows that, and we are looking at laminar flow, right. So if this is the kind of thing that we are looking at, this is the kind of velocity we are looking at, then the coefficient of skin friction, right. So coefficient of skin friction, so like we did come up here, right. So we are using this same definition which we've used earlier, which is this, right, this bit. So we are using this same bit, right. So it is 1.328 by Re based on chord. So this here is basically equal to drag by the dynamic pressure into the area. So in this case, unit 1 is the unit depth into the plane of paper, and c is the chord length. So right, that gives you basically the area. So that is Cf. Now for the drag we have this expression. Basically this is the expression which we are going to use, right. So which is what I am doing, and I am going to kind of miss a couple of steps, right, and I leave you to sort of work through that, and what I get is something like this. The expression that I get is something like this. So Cf is 2, right. So it goes basically from 0, right, to delta by c, right, 1 minus u by u infinity d. Basically we are non-dimensionalizing the lengths by c, by the chord length, as you can see. So you got delta by c and y by c. Okay. So if I get this, and this whole thing is equal to 1.328 by under root of Re of chord. Okay. So if I do that, this is equal to that, and also we know that, if you're already not pointing that out, delta by c is something that we've developed earlier, right. So 5 by under root Re of c, okay, 5 by Re of c. So we're going to use these. So this definition as well. So if I do that, then this, what I get from here is basically this equation 265 n square minus 0.6016 n plus 0.1328 is equal to 0. So, this is an equation which one needs to solve, and if I do that I get two values, right. It is a quadratic equation. So, I get two values of n, which is so n is equal to 2 or n is equal to 0.25 actually, right. I will write it when I can. So, n is equal to 2 or n is equal to 0.25. Okay. Now, so basically I now I can draw the velocity profile. I can draw the velocity profile for two cases. One is 2 and one is 0.25, right. So, if I use that here in this expression here, in this definition of the power law that we were using, we should be able to plot this, right. So, let us see. I mean, this is a drawing which I will do not to scale. So, you will have to bear with me. So, say if I were to do that. So, this is my these lines will need to be straight, and this is not coming out to be straight. Okay, so this is say y by delta, right, and this is u by u infinity, right. If this is so, right, now this is not to scale. Okay. So, this is basically from experiment. Okay, let me write that here. So, this is what we get from experiment. Okay, and what we get from here, right, what we get from here is something like this, something like that, and this one, right, this one is for n is equal to 2, this value, and say the other one is something like that, and that n is equal to 0.25, right. So, basically what one can say from this plot is that this actually does not work too well, right. This power law that we came up with, right, this power law that we came up with to give to take any value of u, that is not holding up too well, given this. So, because it's quite far apart from the experimental value of that. So, one will have to think about a better way of doing this, right. Now, let me so that's one thing to show, and that is also another way to drive home the point that when you come up with a theory, how do you go and cross check whether that's actually even working or not, right. Now, the interesting thing is that, like when I started this, I said you could set up a small experiment to do that. In fact, some of our students have actually done that, and what is interesting is that we did talk about a wind tunnel, right, and having a model there. Now, it will be very interesting that so therefore, what we see is that if I have an analytical expression for this velocity here, then I should be able to get an estimate of drag. So, I tried this, it did not seem to work very well, something else might, you have to give it a try yourself. Okay. But there is another way, for example, if you are in say the wind tunnel, right. So, this is say your wind tunnel, okay, So, yeah, so you have a test section, the kind of wind tunnel that we have. So, it is basically something like this. So, we have an open test section, all right. So, if I were to do that, okay, so something like this, so we will have right, and there is a fan here and so on and so forth. Okay. So, that is the one which blows in, and this is a suction time window. So, if I have so say if I hang a wing model or a 2D model, it depends on what you are going to use. So, say if I do that, okay. Say if I draw a wing model like that, okay. So, that is basically in the test section, okay, test section, and this is going to be hung from the top. It's going to be mounted like that, okay. There is a mechanism on top to do that, and you can change the angle of attack. As you can see, actually right now, yeah. So, actually this is probably the wrong way. So, okay. So, what I mean is, let us erase this bit here. Okay. So, basically I mean the flow is going to come in from this way. Okay. Flow is going to come in, and from what you can see here, that there seems to be a little bit of an angle of attack, does not matter. So, the point here is that one could actually take a little bit of a traverse, and you could measure velocities at different locations like that. As you go on top and bottom of this wing, you could actually take locations and just measure this, just measure it, and then that value, when you input into your equation here, right. So, that should, so that basically then you write this, right, you write this in the form of a summation, right. I will let you do that. I will let you do that. Go ahead and write that. Okay. So, then you go step by step in small steps. Okay. So, you get this, let this be set delta y. Okay. So, you go step by step and you calculate the velocities. Okay. Now, the question is, do you directly get the velocity here, or do you get it somewhere else? I am not telling you that. So, try and think about that. Okay. So, this is an interesting way of doing this experiment, which students can do, and you can actually set this up and get a feel for the drag across the body, right. And it could be any body. It does not have to be a wing or anything. It could be anything. Okay. So, that's one of the things that I wanted to talk about. Also, what I think I kind of didn't mention or forgot to mention. So, what we were talking about the previous module. So, basically what, if I were to sum this up, so drag is a phenomena which is basically contributed by pressure as well as shear forces, right. And most of the times it is difficult to differentiate the two. Pressure drag, foam drag, and is something that is resulting out of the skin friction. So, usually you end up calculating the total drag. So, what we are going to calculate here is total drag, right. So, it is difficult to kind of differentiate the two. Now, as we also talked about the D'Alembert's paradox. So, we used an inviscid theory. Or let us say the inviscid theory is sufficient to effectively calculate the lift, right. And the important thing is that the shear stresses, when you integrate that in the lift direction, do not have a significant amount. They do not have a significant component. So, therefore, the lift is primarily because of the pressure distribution, right, which we can evaluate fairly well with inviscid theory. However, that theory fails if we try to calculate the component of that in the direction of the drag, okay, and hence the paradox. So then you have to take refuge in the viscous theory and hence account for a boundary layer to account for the drag. Okay. All right. So now let us look at another example, okay, and see if we can if this is also another way of kind of slowly it should give you this whole idea, it should give us some idea as to how we are going to use this knowledge, or what are the type of problems we are trying to solve, that we kind of trying to understand this physical phenomenon. Okay. Now, so this is an example. Now, let us say we are going to put it like this. Okay. A thin plate, okay, a thin plate 3.05 meters tall, okay, and 0.305 meters wide. Okay, forms the leading edge of a banner. Towed by an aircraft okay, at 44 meters per second. Okay, so this is the so this is the tow cable actually. This is the tow cable, and this is the thin plate, okay, which is 3.05 meters wide and 0.305 meters. Sorry, 0.305 meters wide, 3.05 meters tall, and it's got a banner. Okay, so basically I can say that it's got a banner, something like that. Okay, you've seen these ones, right? So these banners keep flying and so on. So you've got a banner, and it's got a banner like this, and essentially, so this height, okay, this is L, right? This is 3.05 meters tall, right? And this is the width. So this is the width, which is 0.305 meters. Okay, this is what we have. This is and this part is the tow cable. This is the tow cable. Okay, and you have a free stream. Okay, you have a free stream at 44 meters per second, which comes in, right? What we're going to draw here, okay, we could do that later, but let's just do that for now. So I'm going to draw an axis system. So this is X, okay, this is Z, okay, this is Z, and this is Y. Okay, so this is Y and this is X. Okay, so this is basically the picture that we are looking at. Okay, now okay, so now the question, is, okay, how far from the leading edge of the plate, from the leading edge of the plate does the laminar portion of the boundary layer extend? Does the laminar portion of the boundary layer extend? That is first question, right? The second is, what is the boundary layer thickness at the downstream end of the laminar boundary layer, right? So, what is the, I am not going to write the whole thing. So, what is the thickness, okay, at the downstream end of the laminar boundary layer? So, I am just going to write that, okay, what is delta? And number C is, find the drag force on the plate contributed by the boundary layer and the corresponding drag coefficient. So, basically find the drag and the CD. So, find the drag force on the plate, which is contributed by the boundary layer and the corresponding drag coefficient, which is given is kinematic viscosity, which is 1.52 per second. Okay, so that's basically what we are looking at. Okay, so now, so that is basically the question. So, there is this plate here, and to which a banner is attached, right? And this thing is being towed by an airplane, just like that. So, so what we basically therefore, so when we said this plate forms the leading edge of the banner. So, this is the leading edge of the banner, this is the trailing edge of the banner, and since the airplane is actually towing it in this fashion. So, the airplane is moving this way, right? The airplane is moving this way. So, that we can say that the incoming velocity is, so the incoming velocity is basically from it's 44 meters per second, and it's in this direction. That's the free stream. Okay. So, if I do that, so now how do we sort of go about this? Okay. Now, a laminar boundary layer is expected to transition at around 0.5 million Reynolds number, right? Because now the question is, like I have repeatedly said earlier also, that we're going to use some very ready to use formulae to calculate a lot of things, delta and so on and so forth. But it's very important that you know that what regime of flow are you in the sense that are you laminar or are you turbulent, and use formulae accordingly, right? Because that really determines the drag will be very different if you consider turbulent flow, right? Or for that matter, all the boundary layer parameters will be very different if you consider turbulent flow instead of a laminar flow, right? So, it's very important that we understand that. So, although this is part of the questionnaire in this problem, that how far from the leading edge of the plate does the laminar portion of the boundary layer extend, but that is something that one must cross check or ask every time you do a problem like that. So, in this particular case, so a laminar, essentially a laminar boundary layer is expected to transition. We kind of know this, right, at a Reynolds number of this, right. So, now, so therefore, now Reynolds number I can write, so say some length, okay, u x by mu, right. So, in that case here, so what we know here is we know this, right. So, in this formula what we know is the velocity, free stream, nu is given, and Rex is something that we know, right. So, we can find out the corresponding x from there. So, here x is therefore equal to, right. So, 5 into 10 to the power 5, that is the Reynolds number, into nu, which is 1.52 10 to the power minus 5 by the free stream, which is 44, right. And what we get is 0.17 meters, right. So, how far from the leading edge does the laminar portion of the boundary layer extend? Well, till about 0.17 meters, right, which is kind of less than half of the total width if you want to see this, right. And the next question is, what is delta? What is the delta at the downstream end of the laminar boundary layer? So, at the edge of the laminar boundary layer, and the way we will do that, we know that, right. So, delta, the formula for delta, right, x is basically that is this, right. So, delta x, where did I get this x from? Because you remember the formula is basically delta by x, right, depends on that. So, if I do that, then what I get is 0.0012 meters, right. So, essentially we have a laminar boundary layer extending up to 0.17 meters away from the leading edge of the plate, and the maximum height of the boundary layer is 0.0012 meters, right. Now, if this is so, what is the third question? So, what we need to now do is calculate the drag and the CD. So, let us continue to do that in the next module. The only thing I would like to pull your attention to here is that this is a little different, right, from the plates that we were considering so far, right. The plates that we were considering so far, the flow was kind of always coming, you would have a plate like that and the flow would somewhere sort of come like this, right, and then the boundary layer would develop something like that. But right now that is not what it is, right. So, what we see here is not that. So, you have got a plate like that, okay, and there is a free stream which comes, like this, okay, sort of say perpendicular to the plate. So, what we have studied so far is that the flow velocity is kind of, the direction of the velocity is kind of parallel to the plate, isn't it? And that is what we say, we keep a plate parallel to the direction of flow, but that is not what we are doing here, right, it is actually perpendicular to it. So, please sort of note that, and what we are therefore now saying that a boundary layer is kind of developing this way, over the plate. It's got a very little place to develop it, it's the width of the plate is like 0.305, and then there is this part, which is kind of flexible, so therefore it was important to find out that how far the laminar portion of the boundary layer extends, and what we see is that lies within the plate width, which is 0.305. So, actually we are looking at this very small little distance, right. So, and in that the maximum the delta x, okay, where we take the x to be 0.17, which is the edge of the kind of laminar flow, and that turns out to be 0.0012. Okay. So, about what? About 1.2 millimeters, right. So, let us come back and then calculate the drag and the CD. So, I will close this here. Thanks.